Now, there are certain important examples of the center of mass in motion. So we are considering here in all cases that center of mass is moving. So obviously it must have velocity as well as acceleration. When radioactive nucleus, well, we are using a term here, radioactive. Radioactive nucleus means any nucleus which is emitting radiations like alpha, beta, and gamma rays in its normal state. All elements with atomic number 82 to 92 are natural radioactive elements with mass numbers 210 to 238. But the artificial radioactive elements or transuranium elements are generally having atomic number 93 and it is up to 105 and the mass numbers are more than 238. Now our example is there is a radioactive nucleus initially at rest. So obviously initial momentum will be zero. Now it decays, it disintegrates, that is giving radiations. The fragments fly off in the different directions. When the fragments fly off in the different directions, the particles have different momentums, obeying the principle of momentum and energy conservation. As the decay occurs spontaneously, that is, the decay is not affected by pressure, temperature, or density variations. That is what the meaning of decay occurs spontaneously. No external forces are involved. So when there is no external force, the momentum and energies are conserved. So momentum of the system is conserved as the parent nucleus is initially at rest. Its momentum before decay will be zero. The fragments, that is the parts of the body, the fragments fly off in different directions. When we say they are moving in different directions, means their momentums are different. However, the total momentum is conserved. The fragments fly off in different directions with the different velocities. The vector sum of the linear momentum of all the fragments will be zero. The momentum of the center of mass of all the fragments will also be zero after decay. Hence, the center of mass of the entire system of the fragments shall continue to be at rest after decay. Decay of the parent nucleus into one light and one heavy fragments is shown. So we can just go through the figure. The heavier fragments fly with the less velocity because they are heavy. So obviously their kinetic energy is less. Then the lighter fragments and they are moving in opposite direction with a faster speed. So lighter fragment is shown and the parent nucleus with a dark sphere and heavy fragments in the lower side, light fragment in the upper side. So disintegration of radioactive nucleus is shown in the adjoining figure. Now we take another example, that is moon revolves around the earth and moon and earth system revolves around the sun in elliptical order. So how to start with it? Moon revolves around the earth in circular orbit and the earth moon system goes round the sun in an elliptical orbit. And this is shown in the figure. For the earth moon system, the force of attraction due to sun are external forces. So on the earth moon system, sun will give rise to a force and that will be attractive force, while the force of attraction between earth and moon, that will be internal force, that is the force of gravity. The earth moon system moves along elliptical orbit around the sun due to torque produced by the external force. So earth moon system moves in elliptical path because of the torque produced by the external forces, and these external forces are applied due to sun. So this is what shown in the figure. The center of mass of earth moon system is shown and sun is at the middle. So motion of the center of mass in earth moon system is shown. When an object of the finite size, means which we can measure, is shown with some initial velocity at an angle with the horizontal, it follows a parabolic path. The center of mass of such an object also follows the parabolic path. even if the object were to disintegrate in midair. So the point is that even if the body is in midair and it gets disintegrated or it is turned into fragments, then also we find that it will follow the parabolic path. So it is shown in the adjoining figure, that is OX, OY, and OZ are the three axes, and P is an object and its fragments are shown, but the trajectory is always parabolic. It won't change. So fragments are shown by the dotted lines. So parabolic trajectory of the center of mass, that is indicated by a dark line. Now, cross product or the vector product of two vectors. When we use this term vector product of two vectors, indirectly it will be known as the cross product. Now, cross product of A and B. We are assuming that A and B are two vectors and they're inclined to each other at an angle theta. So the cross product of vector A and B, or the vector product of two vectors A and B, that is defined as. Now there are two figures. In the figures, we have curled the fingers and the thumb is pointing upwards. So there are two diagrams. One is indicating the upside and the other the lower side. AB sine theta into unit vector is equal to cross product of A and B along with unit vector perpendicular to the plane of vector A and vector B. Whenever you write an arrow above the quantity, it will be a vector. Direction is given by right hand thumb rule. Curl the fingers of your right hand from A to B. That is what's shown in the figure. In the left figure as well as in the right figure. Then the direction of the erected thumb will point in the direction of the cross product of A and B. Now there are certain examples. The vector torque is the cross product of R and F, where R is the radius of rotation and F is the rotating force. Then the second example, that is the cross product of R and P gives the value of vector J. Now we come towards third one, that is velocity vector is the cross product of omega and R. Omega is the angular velocity and R is the radius of rotation. Now fourth, that is acceleration. Vector acceleration is given by cross product of alpha and R.